Okay, so when we look at this topic, some of the stuff we have seen in primary school, all the light poles repel and light poles attract kind of thing. And it is still applicable now so the new things that you will encounter is what you see in the picture over here. This basically distinguish, right, what magnetic material is, what a non-magnetic material is. So fundamentally, if we were to look at all these materials in terms of into the particular kind into this particular or molecular level, you will see that things like that has so-called magnetic materials. What you will see is there's a lot of all these little arrows here. All these little arrows, okay, they are also observed as very, very tiny, very, very small atomic magnets. So you can visualize them as having small little pieces of magnets inside your magnetic material. These little pieces here, we call them magnetic domains. So that's just their name. So for magnetic material, over here, you will see that standard magnetic material, we have iron, cobalt, nickel, and their alloys. The most famous alloy that we need to remember is steel, which in chemistry, you have seen this as iron mixed with carbon. Okay, so collectively, they are known as ferromagnetic materials. So they exhibit all this magnetic behavior. So what happens when you go molecular point of view, right? In non-magnetic materials. So for non-magnetic materials, when you look at the structure, there is no domains. I mean, they still have their normal atoms and their molecules and so on, but they simply do not possess magnetic domains. So that's a fundamental difference between something that is magnetic and something that is non-magnetic. And when we look at a substance, or when we look at a pure magnet and a non-magnet, so this is basically a magnet, and when you see the domains arrangement versus a non-magnet, but because it has domain, right, it is still a magnetic material. But even though if it's a magnetic material, it's not able to attract another piece of, let's say, another magnetic material, simply because although if they have domains, they are not aligned. So in a very simple way to understand, right, magnet means that domains are arranged in the orderly manner. When it's a non-magnet, that means they are not orderly arranged. That's all. So all processes, right, that involve the magnetization of a piece of magnetic material, it's just the process of aligning the domains. So when you align the domains, you get the magnets. If the domains are aligned permanently, then you get a permanent magnet. But if they are temporary and so on, right, then you might get a temporary magnet. For example, like an electromagnet. Basically, what electromagnet is, when you pass a current through, you will see the piece of material exhibiting magnetic material. But once the current gets cut off, it's gone. Okay, I think this one you all have some exposure before. So that's the main fundamental difference. Okay, a line is a magnet. Everywhere it's just a normal magnetic material. And if you have now no domains at all, then that is just a non-magnetic material. That's all. Okay, any questions before I move to properties, it should be very fast. Sanjana, have you shown already? Hey, Sejali, okay. Okay, yeah. All right, let's look at properties of magnets. All these are the ones that is quite straightforward. We have things like it says the pole of the magnet, north-seeking pole, south-seeking pole. Okay, simply put it, I think you all have seen this before. Sejana, later after lesson, I send you the ink copy, so you can transfer it back at home to, or you can transfer it back at home when you got the physical copy. Okay, so over here, north seeking. So when the north points to this side, then we have north over here. So this guy, we call it the north seeking pole. Okay, this is pretty straightforward, but there is one confusion thing that will appear when something goes in the some stuff behind that may be a bit confusing. But for the time being, this is what we understand to be a south north seeking pole first. So if you were to walk this way, you'll reach the north pole. So this is a north seeking pole. Okay, and then south seeking pole is the other way around. Okay, then we have this point that says magnetic field. It says it's a region around a magnet where the substance experience force. So simply put it, what's the meaning of like out of the field? That means you're not within the magnetic field. That means the two pieces of magnets, or rather so-called, let's say, the two magnets do not interact. So there's no attraction or repulsion if you're out of the field. So if you're within the field, then they are able to experience attraction, repulsion. Okay, so these are the standard properties together with the last one, which is the light poles attract, light poles repel, light poles, all this stuff. Tiffany, okay? Okay. So so other properties we have will be just the light poles repel and light poles attract kind of stuff. Okay. Now the new thing here is induced magnetism. Okay, what is induced magnetism? In simple terms, I think you all have seen this sort of interaction before. When you take a piece of magnet and it attracts a nail, the nail attracts the next nail, and so on. So this process is called induced magnetism. But what actually happens in induced magnetism? Again, this part here is important for one reason. Induced magnetism, right, is used in the exam, right? Okay, is used in the exam to actually explain. For example, the one of the more popular question is why a magnet attract the iron nail? Okay, for example, okay, we know that primary school method, or rather primary school answer, we say that why is it able to attract? Or we will say because iron is a magnetic material. Okay, that's case closed. Nothing wrong. It is a magnetic material, hence there is this attraction. But when it comes to this question, right, in upper side, we need to explain the mechanism or technically how the attraction takes place. So we need to explain it using the induction process. So this is in very simple terms, if you have a piece of magnet and you have a piece of magnetic material, let's assume for the domains, right? The arrowhead is where the north is, the tail is where the south is. Remember, all these domains, they are fundamentally tiny atomic magnets. So let's take them to be this way. Is it really arrowhead? It's north. We can't really tell. But for our understanding, we will take it to be north, to be at the arrowhead. So when the magnet is brought close to them, the north will start to attract the south of the domains. Okay, the north pole of the magnet will start to attract the south side of the domains. So, and that's because of unlike poles. So at the end of the day, right, what this does is it will kind of arrange the domains that is inside the piece of magnet. So you will get those nearer to the magnet to align first, then this will keep aligning all the way until the whole piece is aligned. So due to this part, due to the fact that the north pole of the magnet attract the south pole of the domains inside there, what we get is that this magnetic material, this thing actually turns into an induced magnet. And in this induced magnet, this part here is south and north. And because of this pole here, there is an unlike pole. And because of the unlike pole, they will attract. And that is how we will want to align our understanding to why a magnetic material is able to be attracted by a piece of magnet. So in a very similar fashion, an example will be example in school, if you all have whiteboard, right? Sometimes there's this magnetic duster where they will stick onto the whiteboard. So in a similar way, right? How does this piece of magnetic duster actually stick onto the whiteboard? Same thing. Okay, the magnet over here will actually induce the domains on the whiteboard. So when they align the domains in the whiteboard, right, the opposite pole between the magnet and the whiteboard. Remember now, after the alignment, the whiteboard is now an induced magnet. So this attraction between the opposite poles cause them to attract together. So do remember, it is not wise to say that it's just opposite. It's just opposite poles attract, or the duster or the whiteboard is a magnetic material. We need to package everything and talk about the magnet aligning the domains in the whiteboard, the magnets aligning the domain in the nail, not the whiteboard, sorry, the magnets. The magnets aligning the domains in whatever magnetic material that you want to attract. We will quote that first, and then after the alignment, it becomes an induced magnet. Then from there, unlike poles ensure, the attraction will take place. Okay, so this is the concept of magnetic induction. Okay, both of you, any question? And as you know, for the magnet itself, when the magnet is removed, the nails fall off because they will lose the induced magnetism. Because the domains will align. Is the reason why the domains are aligned is because the magnet held on to the domains, attracted the domains. So if the magnet is gone, there's nothing to hold them on in a regular arrangement, and they'll be all over the place. Okay, so that's how this whole thing goes. Both of you, okay? Any questions for me? For the induced magnetism? Sanjana, okay? Okay, yeah, all this should be quite friendly. Okay, next, let's take a look at all the methods of magnetism. So under methods of magnetism, we have the easiest way is to use currents. So let's take a look at what is this thing here. It says in a long straight coil of wire. This long straight coil of wire is called a solenoid. So basically, long just coils of wire is a solenoid, and then we have direct currents. Now, direct currents, under the topic of DC currents, you have seen that direct currents are technically currents that flow in one direction, or that flows in single direction. An example of a direct current source will be battery or your cell. This thing here. So currents will flow only in one direction. Okay, so that's the magnetization setup. So over here, question mentioned here that solenoid produce a magnetic field when there's a current flowing through it. What this statement is trying to say is, as long as you have currents in a conductor, this conductor can be wire, can be blah blah, anything. Okay, this combo will always produce a magnetic field. Okay, in real life context, does that mean that every single cable, electric cable that we use, the cable that powers up your computer, the cable that you use to charge your phone, the cable that brings currents from the source to any electrical appliance, does it mean that there is actually magnetic field? When you use a portable charger attached to your phone, is there magnetic field in that wire? The answer is yes. As long as there's a current in a conductor, be it a wire, be it an iron bar, be it anything, there will be a magnetic field. But the thing is, we can't feel the magnetic field. Even if you take a piece of magnets and place close to them, it is likely that you don't experience an attraction or repulsion. And the reason is not because there is no magnetic field present in the conductor. The main reason is the magnetic field is too weak, and that could be possible reason current is too low. So the magnetic field created around the cable is actually not that strong. And that's the reason why, even though there are magnetic field everywhere, As long as there's a current in a cable, you have magnetic field around it. But yet we don't feel it because of the strength. But do take note, as long as you have currents flowing in a wire, there will be a magnetic field. And when you use DC, direct currents, these direct currents will produce what we call a constant magnetic field. Now, this constant magnetic field means that the magnetic field is always in the same direction. That means it's always north on the same side. Okay, so if we were to place our magnetic material over here, okay, you can see that in the diagram, the solenoid over here, there is magnetic field that is produced when the current flows in the coil. Same thing, see all this magnetic field. So as a result of all this magnetic field, when you place a magnetic material inside here, this piece of material can become magnetized. They are being magnetized by the magnetic field that is produced due to the currents flowing through. So what you can see here is the magnetic material that you place in will be induced to become a magnet, because as we know, the difference between magnet and a non-magnet is the alignment. Okay, so the magnetic field, their domains are aligned. You see who aligns it is aligned by the magnetic field produced by the solenoid. Okay, so the simple idea, coil with wire produce a magnetic field. And this magnetic field will align the domains. And when you align the domains, you get a magnet. That's all. Okay, the next point you see here is depending on the type of magnetic material you use. If you use a steel bar, you get a permanent magnet. However, if you use a soft iron, you get an electromagnet. Okay, because it's a temporary magnet. What's the difference between steel and iron? Later we will reach it and we take a look. But as of now, this is the understanding of magnetization. Okay, give you 30 seconds to digest magnetization. It should be very simple about the alignment, about the concept that magnetic field is always present. Yep, help me run through everything once. Thirty seconds, I'll move on to the next part. After this, I'm going to show you demagnetization first. Then I'm going to show you how do you tell from the coil itself, right? Where is the north pole and where is the south pole? So if you understood the concept of magnetization, which is the alignment of the domains, then the concept of demagnetization is directly opposite. You want to mess up the domains. So to mess up the domains, we use another type of current. But before we touch on that, there's one more way that we learn in primary school. Oh, this thing is terrible. Don't do this method. Or to look at the coil on the side and see clockwise and anti-clockwise. This is horrible. We always use this right-hand grid rule. Later we're going to run through this right-hand grid rule. Okay, so before we touch on DMAG, there's one last magnetization method that you did in primary school, which is stroking. So by stroking, just to see whether you all have any encounter with this. Let's say I have a north and south over here, and then we stroke the piece of magnetic material here in this direction. So you'll move up and then you'll glide this way. Tiffany, the one on the left, right? Based on your understanding, is it North Pole or South Pole? North. Sanjana, do you agree? Sanjana, you agree? The North is on the left. Tiffany, how do you decide? Hmm. Oh, okay, okay. So question is whether is it North over here? Yeah. So Tiffany, your approach is correct. Whichever the pole start touching first, that is the same pole that we are looking at. So for example, if this is the bar, and then we have north and south, and we start the stroking in this manner, then this one will be south, following the first point of contact. And if we have and we have a north-south over here, and we do it this way. Again, this is the first point of contact when the magnet is being placed onto this material. So similarly, this will be a south pole. Sanjana, this one okay? Determine the north-south of the stroked material. The point where the magnet touches first, that's the same pole. Okay. Right. So this one, nothing much. So let's talk about demagnetization. So under demagnetization, just now we talked about magnetization, we are aligning the domains. So demagnetization, we are trying to mess up the domain, simply that way. So if you want to mess up the domains, you need to, again, we are going to place it into a solenoid, which is a coil of wire. But the difference is we are going to use an alternating current. Alternating current AC. It means that current actually flows in different direction. And how do you know that you are dealing with an alternating current? Is this thing here. This sine curve kind of design. This is a symbol for alternating current source. Okay, so what's the impact of using alternating currents? So when currents flows in different direction, okay, and AC in a solenoid or in a coil of wire, remember, it is still a current. So current in a coil of wire, they will also produce a magnetic field. Okay, remember the most important thing today is to remember that whenever there is a current flowing in a conductor, whether is it a wire or an iron bar or anything that can conduct electricity, it will produce a magnetic field. And if your current used is an alternating current, that means the conductor itself, your wire, the current is flowing left to right, right to left, opposite direction, right? It will produce a magnetic field, but this magnetic field is actually a changing magnetic field. In the previous example, we have constant magnetic field, where we use a direct current, where the current only flows in one single direction. So because of this AC, it produces a changing magnetic field. That means the magnetic field is not constant. So what this does is, remember, magnetic field can align domains. But when you use a changing magnetic field, the domains will be confused, because at one moment it is following this direction. Then at another moment, when the magnetic field changes direction, they swap again. So they keep swapping back and forth. So they cannot find a constant magnetic field to align them in the same direction all the time. And since domains keep flipping due to the flipping magnetic field, their arrangement will be messed up. So what happens here is the change in the direction of the currents, aka AC. Okay, AC. AC causes this change. This will produce a changing magnetic field in the solenoid. So the solenoid is not constant. So this reversing magnetic field will destroy the orderly arrangement in the domains, because the domains will now try to follow the changing magnetic field. And when it follows the changing magnetic field, it keeps changing direction. So the domains will be messed up. And to mess it up even further, we will slowly withdraw it from the solenoid, pull it out from the solenoid as the domains are changing direction. So you can see this double prong effect. Using an alternating current and at the same time pulling it out slowly. These two combo together, right? It will totally mess up the domains. So if you want to demagnetize a piece of magnet, the easiest answer to use is to place the magnet in the solenoid carrying an alternating current. And if you want to magnetize a magnet, same thing, place the material in a solenoid carrying a direct current. So the only difference is direct current magnetize, alternating current demagnetize. Okay, that's all. So far, any question? I think that should be quite easy. If you have any question, please sound out. Okay, otherwise, the remaining two ways of demagnetization, you can also drop it. Okay, it can be by hammering, hitting it, dropping it, or placing it in heat. All these will mess up the domains. Okay, Ken, any question? Okay, if not, can you all give me 30 seconds? You'll run through this thing again, magnetization and demagnetization. Let me load a YouTube video on how to determine the polarity. Yeah, we'll take a look first. If you all cannot hear the video later, please let me know. We test the volume first. Can both of you hear it? I'll restart the video again. But can y'all hear it? Tiffany can? Jana can hear? Cannot hear? Okay. I changed the setting a bit. Always like that. Can hear now? Can hear? Can hear? Still cannot. What about now? Still cannot. Oh no. Wait, yeah, let me try. I try to change a few settings. The moment y'all can hear it, let me know. Still cannot. Okay, never mind. Then I will. Okay, I will. Still can hear me, right? Well, you. I didn't like cancel myself. Okay. All right. So what actually happens here is, okay, you see this is a solenoid. So we have a solenoid here. Okay, you can see that there's this white column thing. This white column thing is actually just as a placeholder to hold the solenoid, so you can see in a 3D manner. So what happens is that in this particular drawing, we follow the twirl of the wire, which is going like that. So when we draw it this way. So there's a current going out from here later on. Then it will come down like this. Oops. So it goes from the front, goes to the back, and then it keeps going up, going up, going up, and then from the back it comes down again, completing the circuit. So this is how the currents will flow, and this is the simplified drawing for this particular setup. Okay, so this is the twirling that occurs. So how do we use the right-hand grid rule to decide? Is when there's a magnetic field here, where is the north pole, where is the south pole? Okay, I'll let the video run a bit first. Okay, you take a look. Okay, so the card, same thing. The presenter also have their currents in those directions coming down. So you will see that the current move up this way. So the next thing you need to do is see it's very similar. Okay, it's moving up in front. Okay, so you see what he did, he grabbed his right hand. Okay, his right hand grip, right, follows the current's direction on the front side of the solenoid. So you visualize this is like the front part of the solenoid. If you do it in the exam yourself, you can hold your pencil here, and then you just need to know where's the direction of the currents. So the current is going up this way, so you grip it, your fingers following this. Now the thumb here, you notice the thumb points to the left-hand side. So where the thumb points to is the north pole of the magnetic field that is created. So the other side will be south pole. This is called right hand grip rule. So the fingers follow the direction of the currents when you grip it this way, and the thumb will point to the north pole. Okay, so that's how we determine where the north and the south is. Tiffany, okay? Sanjana, okay? Understand this? Okay. So the direction of the currents flow, right, will alter where the north and south is, and the twirling of the wire will also affect. So I'll let him run through the video, then I will narrate as he moves along. But do remember the fingers represent the north. So let me let it run. Okay, so that's where he gets his north pole on the left hand side, and he get his south pole on the right hand side. Okay, now he's gonna do the same coil, but the currents now move up on the right instead. Previously, okay, he's doing the same twirling. Okay, the twirling is exactly the same. Okay, but the difference is now the current is going up. So if you envision, this is the part where the currents will come down. Okay, wait a second. So you see the way he gripped. Oops, missed it. So again, fingers following. You see that in the original drawing, we have the current coming down from the front. Previously, the current was going up from the front. So now, because of the change in current direction, the current is actually going downwards on the front side. Hence, his fingers follow the current's direction, indicating that the current is coming down on the front side. So again, using right hand, you grip your solenoid and your thumb points to the north pole. So for this particular solenoid, you will see that this part will be north and the other side will be south as a result of where his thumb is pointing. Okay. Any difficulty seeing this from this angle? Tiffany, okay? Jana, okay? The gripping part. Now it's gripping the other way because of the direction of current changes. Okay, so let's look at, yeah. The next two drawing that he will draw, right, basically is when the currents, the twirling change. Okay, so let him complete this. So north and south. So the next two drawing on the right, he's going to change the twirling. You notice on the diagram over on the left hand side, you see, on the left hand side, it goes from the front to the back, and to the front to the back. Whereas in this drawing that he's drawing right now, he goes from the back, twirling it to the front. So he's reversed the turning. So previously it was turning in okay, put it this way, one is turning clockwise, the other turning anti-clockwise around the piece of material there. So what we have here will be opposite twirling. Okay, let's take a look. So the twirling is now opposite, but he's going to do the same thing. Okay, he's going to place the currents going up on the left first, just like what he did on the first diagram. So the current will flow down, 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 and down. So if you do your right hand grip rule, you will see that north is over here, south is over here, because the current is coming down from the front again. So north will be on the right hand side. So that's how came up with north and south. So the last one will be, again, reverse twirling from the left, but now the current goes up on the right hand side. So you have currents going up from here, coming down from here. So visually, you will see that the current is moving up from the front side of the bar. So if you do your right hand grip rule, see the fingers will follow. Okay, so the fingers will follow through to get something like this. So in a similar way, you'll get your north and your south. Okay, that's all. This is called right hand grip rule. Is it important? Yes. Very, very important. Okay, so it's just reiterating what he has done. So when current goes up this way, yeah. Okay, I believe you all have seen before, right? If this is a piece of magnet, how do you make the magnetic field stronger? I think lower sec or primary school might have done this before. St. Joanna, what say you? What do you think you can do, right, to increase the strength of the magnetic field produced? Okay, how do we increase? Okay. It's so-called to increase the strength of the magnetic field. Okay, mention number one, you mentioned about adding more coils. So normally you say increase the number of turns. Tiffany, what else can you do to increase the strength of the magnetic field? Add more batteries to the circuit, correct? When you add more batteries to the circuit, what do you effectively have done? What do you increase? That will directly affect the strength of the magnetic field. Increase voltage, then ultimately, right, the term that we want to use, right, is it will increase the current through the wire or the solenoid. Okay, through the solenoid. Okay, number three, right, is we say we insert the so-called soft iron core. Okay, what is inserting of a soft iron core? Okay, even remember we say that when current is flowing in a coil, right, or flying or flowing in any conductor, it will actually have a magnetic field. Whether or not, right, there's a piece of material inside there. So that's why at the beginning when he was using his this plastic coil over there to hold the wires, right? Will there be magnetic field? There will be magnetic field. Even if it's a plastic coil, it doesn't matter. As long as there's a wire, there's currents, there will be magnetic field. But if you want to power up your magnetic field inside your coil, instead of putting in nothing or placing in a non-magnetic material, you place in a magnetic material like iron, then your magnetic field, even without increasing more turns, even without increasing the current, by using a core, by using a soft iron, you put the iron through the solenoid, you actually increase the strength of your magnetic field. But of course, the setup must be able to accept the core, because sometimes you see the drawing given to you, right? You cannot insert the soft iron core already. So when the question asks you for how do you increase the strength of the magnetic field, then you can say number of turns or currents. These two are the most common ones. Okay, but what exactly does it mean by insert a soft iron core? Okay, it is this one. Let me put it here. Let me put it here. Okay, he's going to insert a soft iron core. You see, this is a soft iron, and literally he's slide it through this. This piece of plastic here, no meaning, it's just to hold the wire in place. So by inserting this soft iron core into the solenoid, you actually power up your currents. You actually power up your magnetic field, even without adjusting coils or adjusting current strength. Okay, so two things from this page here so far. Number one is, how do you use right-hand grid rule to decide where is north and south? And number two, how do you increase the strength of the magnetic field produced? Okay, Tiffany, all right? Jana, all right? Any questions, Jana? Okay. The main thing here, the main new thing is actually the right-hand grid rule. Okay, let's go back to the notes itself. Okay, so you can see here, if you use your right-hand grid rule, you use your fingers to follow up. You'll see that your fingers will be like this. Your thumb will be here. So the fingers follow the current, the thumb points to north. Hence you get this. Something like that. Okay, so that's all. Okay, let's look at this portion about temporary and permanent magnet. Just now I talked about a lot about soft. What is soft? Okay, first off, in terms of soft and hard, we are talking about soft magnetic or hard magnetic. So for temporary magnets, for example, normally we use soft iron. Soft iron, as the name suggests, right, is a soft magnetic material. And the example is iron. Okay, what does it mean by soft? Soft means that the piece of material, in this case iron, can be easily magnetized and easily demagnetized when current is switched on or off. So this is a very good way of activating a piece of magnet very, very easily. The moment you turn on the current, it gets magnetized immediately. There's no delay because it is easily magnetized. But at the same time, when you switch it off, it will lose everything. Because for this kind of soft magnetic material, okay, for soft iron, it is so-called, we'll say that it's unable to retain magnetism. Okay, and that's why we would use soft iron if we want to do applications where we can turn on and turn off magnetic field easily. And application for this will be temporary magnets. A very easy way to understand this is, for example, this is used in recycling. So, for example, in a recycling plant, you have if the trash are not sorted out, if it's just general trash, right? There can be glass, there can be paper, there can be iron, there can be steel present in the scrap. So what they can do is lower an electromagnet, turn on the current, it gets magnetized really quickly, goes into the pile and attract all the scrap iron. Then the electromagnet can transfer to the storage or the loading area, switch off the currents, loses the magnetism straight away, and the scrap iron can fall to somewhere for storage. So that is a very good application, right, so-called make use of the fact that iron cannot retain magnetism. Okay, something like this. In another case, if you want a permanent magnet, then basically all the magnets, permanent magnets you see at home, they are all made of steel. And the reason why we use steel in terms of permanent magnets, because the important thing is it is able to retain magnetism. But the problem is it is hard to magnetize. So if you use a steel bar you put in a solenoid, immediately you put it in, will you get it to magnetize straight away? Answer is no. For the first maybe 10 seconds, 15 seconds, 20 seconds, 30 seconds, you will see that there might not be any magnetization going on. There is very, very minimal magnetization because it's very hard to align the domains in materials like steel. So again, as opposed to iron's domains are easily rotated around. So when you have currents, they align very fast. You don't have a current, it goes away. But for steel, it's another way. Once it's very hard to move them, but the moment you move them, it is also very hard to let them go back to their original position. And that's the reason why they are very, very good choice as a material to make permanent magnets. Okay, so the difference between soft and other materials, other magnetic materials, sometimes we can even we'll call this sort of material to be hard magnetic. But again, depending on whether your teacher using it or not. But hard magnetic and soft is just a difference between can retain, cannot retain, easily magnetize or very difficult to magnetize. That's the main difference. Okay, any question? If not, I move. If not, those who are okay, can we move on to the work example? Let's just take a quick look at this work example. Then we move into the questions. Okay, but give you all a minute to digest this and look at this work example here. Anyone with question, please sound out. If not, look through the work example. I will go through in a minute. Okay, let's look at the work example here. So one of the more important thing is, for example, in point A, I say describe what happens when the iron is placed under. Do remember to say we look at the answer in point A, the magnet induces the iron to become induced magnet. Okay, it's because of the induction, then they can attract each other. And then for the nails between X and Y is almost the same. And the main reason also because iron is a soft magnetic material. And because it's a soft magnetic material, they will align very easily. So that means the piece of the little piece of iron over here. Okay, this piece of iron over here, we will get aligned very, very easily. So the strength will not be compromised. So they have roughly the same number of nails, which compared to Z is a lot lesser. So why a lot lesser? Definitely the piece of plastic, it acts like a barrier like that. So the piece of plastic is kind of similar like distance. So now because of the piece of plastic, the magnet is a little bit further from the iron nail, so that actually weakens the magnetic field interaction. So as a result, they don't attract so many. But in all cases, it's the same thing. If you remove all the magnet XYZ, everyone will fall off. And why everyone will fall off? Because there is no steel head. One of the piece here looks like this. Let's say W. If this is a bar magnet, and this piece here is iron. Sorry, steel. At time equals to 0 seconds, immediately. Immediately when the steel is brought close to the iron nail, right, you probably have little to no nails. And the reason is because steel is hard to magnetize. And because it's hard to magnetize, the attraction is very weak. So there's very little nails or even no nails attracting to it. But time equals to infinity after a long time. If you actually remove the magnets, the steel continue to attract the nails, and it's because of its ability to retain magnetism. Whereas in this case, if this is removed, okay, if the magnet is removed, all the nails fall off. Because for your iron, we say unable to retain. Okay, so these are the things that y'all got to spot in the exam. Difference between iron and steel. Okay, if y'all have no question for me, can we look at revision 1? Okay, I'll leave this for anyone of you who need to copy anything. Otherwise, can we look at revision 1? Time now is about 8:46. Can we try to finish by 8:55? Then we go through slowly. Example, the entire revision 1. And then we go through together. Let's give ourselves 10 minutes to do. Should be quite easy only. No need to do long answers. Just scribble the concept and we'll do. Along the way, anything stuck, please let me know. Okay, so this one practice and see if you know how to do the right hand grip rule. This is exactly the same as what you see in the video. I send you all the link to the video that we see just now. Okay, 8:55, we'll go through the whole revision 1. Yeah, by the way, since this is our final year already, the our main focus is the real exam at the end of the year. So right now we have about 40 weeks to go. Similarly, if you all face any difficulty with, let's say, school or anything, right? Immediate rectification, please WhatsApp me. Otherwise, things that we cannot settle through WhatsApp, we come online to do it. Okay. Normally I give a lot of priority to Sec 4s to clear that stuff. So again, target is to finish syllabus by April. We should be able to finish by April. Oh yeah, Tiffany, once you know what you are doing, you let me know, because I think you only left a little bit, then it's the rest of the electricity thing that we did. I can't wait for all your respective schools to finish syllabus because it's too late already. So by April, we should be doing revision papers. Oh, you have your SLW already? Okay, Tiffany, please send me. The Jana, yours is like what we discussed yesterday, all the electricity stuff only, right? Everything else all clear, just to confirm. Okay. The static, I feel like all the topics that you'll be doing, static could be one of the harder ones at the beginning of the electricity part. So in the event you have any issues, please come back to me immediately. So Tiffany, same thing as yours. Whatever that you are doing, any difficulty, you'll try to come back to me as soon as possible. If anything that we need, we sort it out. I mean now, at home studying, it's a lot easier. Even if we log in at night 11 o'clock also can. I mean, provided you're not sleeping. No, we can do that. So ultimately, hey, please get your distinction. That's all I can say. The only thing that I can help you all minimally is practical. I can't give you all practical experience. So, I mean, in terms of certain answering and things, maybe I can help you, but the actual execution, you still got to follow closely to what your teacher says. But otherwise, yeah, take charge of things that you don't know and come back to me ASAP. We should be good. But this year schedule is super packed. Almost every day got lesson. So if you all need any extra help, let me know earlier. And most of the time, evening lessons on the weekday is like at 7:30 to 9. So if you all need any help during the weekday, it's either you all see me before the class if you all are back home earlier, or after 9 when the classes are done. And homework submission will start somewhere where we finish syllabus, somewhere in April. So we'll do 1 or 2 O-level paper to boost morale a bit. Then I'll destroy you all with the school papers. So that's the plan. Oh yeah, another thing, if you're able to get it, go and get the latest TYS or yearly arrangement. Don't get the topical one. The topical one is not useful for us now. So if you all can, go and grab the yearly TYS from units. Yeah, then we'll work on that. Okay, let's go through the division 1. Okay, this is my true false. Settle 1A. Ferromagnetic materials are metals, true. They are all, this is the true statement, but this is the false statement. Is it true that all metals are ferromagnetic? No. Only the iron, cobalt, nickel, and their alloys. So statement A is not true. Statement C is not true. A substance is permanent. It can attract another magnet. It says a substance is a permanent magnet if it can attract another thing, if it can attract another magnet. True or false? Okay, so if this thing here is unknown, this is a magnet, we know it's a north-south. If they attract, that means he's a magnet. Answer is no. He could be just a magnetic material. Okay, the best choice is always to go for repulsion. Repulsion is the proof for magnets. Do not go for attraction if you can. Okay, let's talk about magnetic field. Okay, so as you mentioned, it's the zone where they will feel a force. So generally, cut and paste from the notes in front. Okay, region at which magnetic material experience a force. Oh yeah, homework wise, forgot something. The homework is need to submit for marking. Tiffany, last year I didn't really ask y'all to submit. We just do the practice only. But this time round, I need y'all to submit the homework. So need y'all to do I'll still mail y'all the hard copy. But if y'all prefer the soft copy and then you can work with the soft copy, right? You can let me know also. Because some of you can use your iPad or whatever, then you can use your soft copy to send over also. Also can up to you, whichever version you prefer, you let me know. Yeah, because you need to eventually send it back. You need to send back to me for marking. But I think hard copy easier for you all to do work and write notes. So you just let me know by then. But you all need to somehow convert your hard copy answer and mail it to me. Don't take photograph. If you can do, can scan. Okay, question 2B. What happens when two magnets are placed on the same pole? This one very simple, repulsion. Okay, solenoid. Just now we mentioned solenoid by definition, long coil of wire. Okay, long straight coil of wire, solenoid. Okay, so what happens when you place soft iron? This is the one that cannot retain magnetism. So this thing turns into an electromagnet. And if you put steel, which can retain magnetism, it becomes permanent magnet. Tiffany, where's your North Pole? Yeah, if you do your right hand grid rule, this is north because your thumb points to that side. This is south. The journal got it also. Fingers following the currents, thumb points to north. Okay, great. So what other ways to make it a magnet stroking? Okay, we will stroke the bar using a magnet. Okay, I'll leave this here 30 seconds and move on to the next page. Well, Tiffany, do you know when you will step down from CCA? Jana, also yourself, do you know when you step down from CCA? Okay. Three applications for your permanent magnets. Okay, all kind of based on from all the speakers, dynamo, all your generators, motor, and all those stuff. Okay, I'll just leave it there. Okay, number 4. Or I just text y'all to put a tag there so I roughly know when y'all can be abused more. Okay, question 4. Process all this new attract new attract new induction. So the process we will call it magnetic induction. So polarity, P and Q, we have north attract south, south attract north. So this part of the head of the nail should be north. This one should be south. So PQ should be north and south. And the last nail should also be north and south. So our P will be your north pole and Q will be your south pole. Let me save first. Okay, what happened to permanent magnet when it's removed? Okay, we'll say that the nails, because they are iron, right? So the nails will actually fall off. Okay, you need to mention that because in this case it's made of iron and is unable to retain magnetism. Okay, and the last portion, permanent magnet placed inside a solenoid with an alternating current. So alternating currents, solenoid, this is demagnetization. So we say that the permanent magnet will be demagnetized. And two other ways, we can either hammer it, okay, literally hitting it, dropping it, or using heat to hit it. Okay, all these are all possible choices. Okay, today first lesson, I didn't plan very complicated stuff, just to wake up ourselves. Okay, so okay, just a quick look what we are doing next week. So next week we'll be drawing all these diagrams, all these few line drawings around the magnetic pole and how the different magnets interact with each other, how to draw all these few lines, and then how to use a compass to draw the few line and all. Then basically this topic is just like that. But one more thing that I will also want to mention is, Sanjana, were you around just now or you were bumped up when we talk about this north sitting pole thing? Were you locked out temporarily when we were doing this? Or were you around? It's okay. So we'll do this thing again to talk about Okay, after because this thing has a strange issue. After we integrate it with the few lines, after we integrate the few lines. So I just put a note here to revert back to north-seeking pole. Why do I want to do this? Is it in syllabus? No. But it came out in O-level once. So that one, quite a bit of us was caught by it because we didn't expect it was there. So anyway, we will look at it next week. Then we'll finish up all this. And the last part will be, these are slightly hard questions for magnetism. We'll finish up with this and then we move on to the next topic. Plus, the next envelope that I sent you all should be the next two topics, plus whatever that you are doing and you all might need. This one I'll arrange you all personally. Okay, other than that, if you have no questions for me, thanks for coming, everyone. I'll see you all next week. Good night, girls. Bye-bye. See you, Sanjana.